So now how can we be sure that our minimizing the training error will lead to a better model when applied to the test set? So this is an example, an intuitive example from the machine learning literature that actually aims to illustrate the concept of overfitting and underfitting. So suppose we have a set of data sets of trees and other objects, other botanical objects, or the flowers, etc. And we want to be able to learn the concept of being a tree. So we could use a natural language in statements. So we could come up with just sentences that tells what's a tree from what's a non-tree. An example of that, we could come up with a sentence that tells a tree has a brown bottom part, right? And a green top. So this describes a tree, but however, if the data says that we have also bushes and other things, some other things can be mistaken as trees while they are not. So this is a very general, actually a very general concept. This is general concept, general description of a tree. So this is our first function, F1, that describes what's a tree. A second possible function describing what's a tree could be, let's give as much details as we can about the tree. So it could be that this tree is 5 feet long, and actually this tree has 3 roots and has 4 major branches. And we could go on describing very specifically what's this tree, maybe the shade of brown, the shade of green, and let's say, and the 50 leaves, etc. So I'm going to provide a very, very specific description that tells what's a tree. The trick is that this description would match this tree exactly. So it will be actually fitting this tree perfectly, which means that if we have other trees in the data set with other variations, with other features, maybe they have 40 leaves or they have 4 roots, these trees won't be classified as trees using this second function F2. So this is too general and would let many non-trees be classified as trees, and this is a very specific description that will let actually no trees be classified as tree because it's so specific to this specific tree here. All right, so the idea of machine learning is to explore everything in between. What would be the sweet spot, the best hypothesis or the best function, F, right? I'll call it O for optimal. What would be the best optimal hypothesis or description that tells me what's a tree? So maybe you could do something in between in which we specify what's a tree, but without really going too general to specific. So it could be like the bottom is a trunk, the bottom is woody, right? Is woody with between 5 and 7 feet. We could say there is lots of leaves on the top, lots of leaves. It has branches. It has between 3 and 10 roots. This is something more general in which that would let pass many trees, but would also not let pass bushes, because bushes are probably shorter in the terms of the height of their trunk, and so on and so forth. So between the 3 hypotheses, we would prefer then picking up this one because it has more chances to make less error in predicting that an object is not a tree or an object is a tree. At the core of machine learning is what we call structural risk minimization, which actually aims to find the best possible models given some problems. So on the x-axis, what we have here is the complexity of the model. So we have a set of models going from the very low complexity models to very high complexity models. So for example, the model that tells that the tree has a brown bottom and a top green is a low complexity model. It's very simple. The other one that has very specifics about the number of leaves, branches, and so on, is a high complexity model. On the y-axis, we have the prediction error. And here we consider the error on both the training set and test set. So I'm going to plot 2 curves, one for the training set in green and the test set in red. So I'm going to see the behavior of the error when we vary the complexity of the model. So you could expect that with low complexity models, such as our simple sentence about trees, we're going to let lots of non-trees passing as trees. So we're going to make a lot of mistakes, which means that the prediction error will be quite high even for the training set itself, right? We expect it to be also high on the test set. So if it's not doing well on the training set, it's very likely that it will do poorly on the test set. For the high complexity models, we actually, in the example of trees, our model will be able to match the training set exactly. So we are going to really find a model that overfits or learn by heart our training points. So the training error will be quite low because we really learned exactly what was on our training data. However, when we plug this function f into a new data set of trees and bushes, etc., we're going to do poorly because the complexity of the model was so high that it wouldn't let any other tree make it through the test error. So basically, we would have a high test error and a small training error. The art of machine learning is to find something in between. Good models would be somewhere in the area in the middle, in which you don't what we call underfeed the data by making poor models in the terms of they are too simple, and we won't overfeed the data because your models will otherwise your model will be learning your data by heart. So how to find a good model? Something in between is at the core of machine learning methodologies. Okay, so let's illustrate this concept of training and testing and structural risk minimization with respect to this example on regression. So suppose we want to predict the income in function of age, right? So remember, we have plotted the data as data points on a 2D space. And the idea is to find different functions or different prediction models that give us a prediction of a future instance. So for example, this line here is a linear model that goes through the data points, or this second curve in blue, or also this complicated curve here. In the first example, we talk about underfitting or high bias because this line does not really fit well the data. In the last example, we talk about high variance of overfitting because we came up with a curve that actually goes through each and every single data point in the data. We really learn the data by heart, and it's not a good model either. So the two models are going to be on the extreme sides of the structural risk minimization curve. The third one is more promising. It's just right. We find something that goes through most of the data points but doesn't fit them very well, but it doesn't fit them poorly either. Okay, so how do we avoid underfitting and overfitting in general? To avoid underfitting, we need to find models that at least do well on the training set, right? So this is easier than avoiding overfitting. To avoid overfitting, what we can do is, in general, try to avoid complicated models. If you remember, we find this complicated model that describes trees. This model will make poorly on any other object except those seen for training. So in general, use simpler model. And the way to use simpler model is, for example, to reduce the number of features. For example, if we don't look at the number of features for trees would be number of leaves, number of branches, number of height of the trunk, and so on and so forth. So the more we're going to put in the training set, in the feature values, the more the model will try to include all of them. So what we can do is to remove some features to avoid really finding models that would use all of them. We could also do some model selection, and this is something that will be left for the machine learning course. We could use what we call regularization, which is, okay, so we have lots of features describing the data, let it be. Let's use all of them. However, let's reduce the importance or the impact of this, the small parameter values. So if you have a lot of features that contribute a little bit to the model, let's try to regularize that. So we're going to make a balance between learning the data and also having all the features having an impact on the, reduce their importance in the final model. The last possible things we can do is to do what we call a cross-validation, which is to estimate the test errors, and we'll see in a bit what this means.